I'm going to talk about history, so it's been written on an old papyrus roll here, as you can see. And you know that these papyrus rolls stay for long, so it's hope that this will stay for long. I will talk about something which is, which in the beginning looked like a very different approach to physics than the Young-Mills theory. But you will see that, all roads lead to Rome. In a sense, you see that all good attempts in physics would lead to Young-Mills theories. And this is, so it's mainly, as I said, a historic talk. Oops, what do you have to get? So we know, that we talk about in the 1960s. It was great for particle physics. We got all these SU3 of flavor, quarks, SU3 current algebras. And it was the beginning of the Standard Model. There were hundreds of new particles. And it was a very exciting time in that sense. There was so little was known. So how to describe the strong interactions was a big issue at the time. And even though the quarks were there were no quantum field theory for quarks. And there was the S matrix was then a very popular bootstrap. And Jeff Chu was the leader of this movement. And of course, another thing that happened was that one looked for a theory described directly in terms of baryons and mesons. Then in 1968, there was a proposal for an amplitude by a young Italian guy, Gabriele Veneziano. And look at his the title of the paper. It's a bit Italian in symmetric. Beautiful. So he wrote down an amplitude for pi on to pi omega in terms of beta functions. Of course, this is completely different from what you do when you do a field theory. You start with Lagrangian, you do propagate, you do whatever. Here it just wrote this expression, and it satisfied a lot of nice criteria. One was that the amplitude satisfied duality. And duality was the same, that you could either describe the amplitude in terms of, does this work? Where do I push? Someone? Either in the S channel or the T channel, it should be the same. And this is very different from what you're learning in quantum field theory. So it was realized it could only be done with infinitely many poles. So these were very far from Feynman rules. But still, it was interesting enough that it became very popular. And there was a race started to construct more amplitudes. And so that this race was somehow won by Corbijn-Nielsen, who could write a general n meson amplitude in terms of this expression here. Again, this is a closed expression for, well, you would still say that it's a first order in some coupling constant. But you see it's written in terms of some fake integration variable here. And it doesn't look at all like what you learn these days, when you study quantum field theory. And, this was for n amplitude. So a good question was then, could this be written, could this be factorized? What we remember from, also from ordinary amplitudes. And yes, Neveu and Fubini, Gordon, Veneziano found that one can write it like this, So this looks like now like a Feynman diagram in a sense. You have propagators here, but it had hidden in itself other propagators, because you could dualize this. You could use this rule that I was talking about before up here. For any sort of subset of the diagram, you could do these things. You can see that one diagram here describes lots of channels. And one can even construct or connect this. First attempt, I think, was done by Kikawa, Sakita, and Virasoro. And so in a sense, it looked like more like other theories. But what kind of theory was this? Well, these three gentlemen, Neveu, Nielsen, and Susskind, very early on said that this was strings. And there is a beautiful sentence by Neveu in a conference on symmetries and quark models at Wayne State, 1969. And it says, equation 17 suggests that the internal energy of a meson is analogous to that of a quantized string of finite length. So this was sort of the first statement that these had something to do with extended objects. So a popular way of drawing these diagrams, and if you remember when David talked, he was saying that like a meson was like a string with some force field in between, was to think about it like this, that you have, what did I do it? Two quark, anti-quark, coming in here, and then you can see that you can then interpret that either you can push it in this way or that way, and you can see that this kind of diagram should be able to describe poles both in what we call the S channel and the T channel. So this is all fine, and then people started to try to use this. And Hongmu was the champion at CERN to try to see, can we fit data with this? And he got lots of people, and they were working very hard. And there was, evidently, there was some success. There was certainly something in it. This was a very promising approach to do strong interactions. But, still it was hanging very loose. What kind of theory is this? Well, strings, but what is the underlying theorem? To make it even more complicated in a sense was an observation that Miguel Virasoro did in 1970. He said that if we now instead look at a theory where, so I should say that all the particles lying on linear trajectories like this. But he said if you push the trajectory up so that the intercept here, the first particle here, is a massless spin 1 particle. But at that time, we believed that it should be a row meson, and then it should be 1/2. The real physical trajectory went through here. But if you make this, as I said, this very unphysical assumption that it was a vector particle instead, then it opened up an infinite symmetry. And here you see the first connection with Young-Mills. Here it's a massless vector particle. It seems to play a crucial role. Or turn it around, if you use massless vector particles, you get a much bigger symmetry. And we love symmetries, as you know. So from that point on, it took, now this became more of a theoretical investigation, because somehow these models that seem the most, shall I say, promising ones, didn't seem to have anything to do with nature. One aspect of these diagrams was that I said you can draw it like that. This is what Neveu and Veneziano Fubini and Gordon had said, let's say this is a 6-point amplitude. You could somehow pull it around. Think about this as a string, you know, you can just, or a rubber band, you move it down there. However, if you look at that one, it seems as you are twisted, or rather, if this is a meson field here, and somehow, if you then twist it up, you would have some other kind of propagator here. And one could at that stage write it in terms of a vertex and a propagator, vertex, propagator. This had to be a different kind of propagator. And so Claude Lovelace in 1971 said, let's try to compute this diagram. Well, no, the ones who had, I turn around. David, with his colleagues at Princeton, had computed this with these naive rules that one had at that time, but you could see the structure of it, and they found that this introduced cuts, branch cuts. And this was, of course, killing for the model. So it didn't seem to be working at all. And then Lovelace made an observation, which was rather, people took not very seriously. He said, if the correct procedure, no, he said, correct, well, if the correct procedure give the correct, I'm coming back to the measure because the measure was a problem. But if you forget about that, and he said, if there were 26 dimensions of space-time, the branch cut turned into new poles with trajectory having intercept 2 and slope 1/2. Of course, few people took this result seriously. 26 dimensions seemed to be a very odd number. 26 doesn't really strike you as any fundamental number. 2 times 13? No. And even Lovelace used this as a joke. And it's funny, you know, that in the 1920s, Kaluza and Klein have been talking about higher dimensions. But that was completely forgotten in the beginning of the 70s. And just as a funny thing is that when I came to Caltech later in the 70s, we had to learn to pronounce Kaluza's name in Polish because Murray Gell-Mann was very particular with languages. He didn't know, nor did we, that the family Kaluza had been Germans for several generations. Anyhow, but this was, of course, interesting. Intercept 2. That sounds like a graviton. And we realized that. However, for the moment, this was just a funny fact. I have to give you another ingredient in this game, and that was that these 3 young people, Ramond, Neveu, and John Schwarz, they discovered also how to introduce fermions into this picture. And with that came supersymmetry, spinning strings, supersymmetric strings, and finally the superstring. Also, this was the time for the Nambu-Goto action, where it really could show that you could start with a relativistic string from a Lagrangian point of view and derive the properties, the states of the theorem. So here, things were developing, but they were developing in a way that people had started was not really happy with, because this became much more theoretic. But as I said in the beginning, you know, it's important to follow a good idea. You have to follow it through. You have to see what does it lead to. Also in 1971, Joël Scherk asked the question, what happens if you take the slope of these trajectories to 0? That, if you go back to this expression here. What happens if we just tilt them like that? Well, what we do is that we push these particles away out to infinity. And we are left with just the fields here. So in the beginning, well, he thought I had got a lambda phi cube theory. But for the first time, you see that it's connected to quantum field theory somehow. Then it was not completely correct. So together with Neveu, they found that, in fact, by doing that, you can get a Young-Mills theory. You get it in a funny gauge, but it follows all the rules. So this theory, which came from some very different aspects, had in it a Young-Mills theory. I would say that people were quite surprised about that at the time, especially people who were had grown up with quantum field theory. The funny thing is that this field was pushed by a set of very young people and who didn't know enough, to worry about what we were doing, which I think sometimes is good. So, in 1972, it was proven by Brouwer, Goddard and Thorn, that this theory, in fact, had no ghosts, which is a strong indication, if you now think about it, as it must be some kind of gauge theory. Because the beautiful thing, which we haven't talked too much about in Young-Mills theory, is that you introduce 4 vector fields, but you have just 2 degrees of freedom for every color, say. And these people took Nambu's and Goto's action and really quantized and showed. And they showed that it was only working in 26 dimension, but in 10 dimension for the supersymmetric version. So we who worked in it at that time were very ecstatic, but outside, people were laughing at us. So at that time, my collaborator David Olive and I, we said, let's try to really formalize. Let's see if we can do this carefully and really see if this is a model which is working. And with some help from Scherge and Rebbi, we found the final proofs that the Ramond and the Neveu Schwarz model, they really unite to one model. And there are no ghosts in either sector. So that theory was really working. Before it was really 2 models. And we also had a rule, we could compute loops, and we understood how closed strings came from intermediate state. So we had united open and closed strings consistently. Now we had a theory which was unitary to this level, which had open strings and closed strings. That meant that it had Young-Mills theories, and it had gravity theories in it. And the technique we used to do these things was a technique that Feynman had used once he quantized Young-Mills theory in 1963, namely something called the Feynman's tree theorem, which is a beautiful technique by which you can, by knowing the physical states and by knowing the tree diagrams, you can construct loops. So anyhow, the only problem at that stage was that this model was ghost-free but contained tachyons. And I should say that by this time, we had got Weinberg's lamp, scaling, QCD, and asymptotic freedom. So most people left the field, and we were left there. And of course, people left for good because there was this tremendous development that David talked about before with QCD, which completely, changed the picture that now we had a theory for the strong interactions. And what we have been doing in this other attempt was something completely different. And but we were a few diehards, and we were looking, we thought, that the only problem was that we had not been able to go from 10 to 4. We had 26 then. And could we construct a theory in 4 dimensions? And eventually we succeeded. However, it was a theory with 2 space and 2 time dimensions. So So it didn't really work. So the alternative really was that we were barking up the wrong tree. This was just some attempt to, this was some beautiful recreational mathematics, as people have said. But of course, a thing that we have been discussing all the time, which was more formalized first by Unea and then by Wess and Zumino, was that string theory is not a model for strong interactions, but a theory for gravity and Yang-Mills. And by doing that, you know, it was a different ball game. In 1973, of course, Wess and Zumino developed supersymmetric quantum field theories, and they found that they had improved quantum properties. That was a very important step. Supersymmetry had been before discovered in the Soviet Union, and it was known in 2 dimensions, starting from the work of Ramond. But they were pushing it to 4 dimensions. And year after, Ferrara and Zumino and Fayet, they developed supersymmetric Yang-Mills theory. We heard about Fermi boson symmetries before, and that was shown that these theories had better properties. So in a sense, this was, of course, this was coming from the string theory approach, but it was quite independent. By 1974, Gell-Mann had classified all supersymmetric algebras, and he started to talk about the limit n equals 8. He never wrote it up. In the literature, it was discovered by Nam. But I happened to be at Aspen in the summer of 1974, where he was talking about the whole, every lunch he was very excited about it. This led to, in 1976, that Friedman, Van Nieuwenhuizen, and Ferrara and Wess and Zumino, they discovered supergravity. So that they took the idea of a supersymmetric Yang-Mills theory to a supersymmetric gravity theory, where you had the local reparameterization invariance and the local supersymmetry. And they started a new industry in theoretical fortune. And here, relativists and particle physicists were joined. But at that time, you know, we had come so far from string theory. So the people who came in, they had not really worked in string theory. So John Schwarz and I joined in on supergravity, but we had this, we knew from our work in string theory that, you know, there were these special dimensions, like 10. And also, Shaq and Paris had this. We had this huge advantage. So we knew then, from this work that we have been doing, that there existed supersymmetric Yang-Mills theories and supergravities in 10 dimensions. In principle, it was this technique I was telling about of taking the zero slope limit. So we said, let's investigate this Yang-Mills case. And so then the remarkable thing, it's just another remarkable thing about Yang-Mills theory. This theory, which looks like, so this is the ordinary Yang-Mills term, and here is the fermion case. And this here, like that, you can write in 3, 4, 6, and 10 dimensions. The same expression. It's a different, I mean, here it means that this has to be 3, 4, 6, and 10. The gamma matrices here have to be, you know, in 3, 4, 6, and 10 dimensions. And the spinors here have to be the lowest spinor representation of those dimensions. And you can even write the invariance here, like that. It's the same in all dimensions. This somehow shows that this theory has a beautiful symmetry under it. And this is what I was hinting at also when in the beginning I was saying that in mathematics, the Yang-Mills theory has been used so much. So this theory, from the start we were really finding that it has all these beautiful properties. So then what we did was we take this theory and we go down explicitly. We start with 10 dimensions and put these coordinates to 0. And then we can write this theory like that. It doesn't look so beautiful. And the symmetry doesn't look so beautiful. But it's the maximal theory written in 4 dimensions. And as such, we left it there. It was a beautiful theory. But what was it to be used for? Then in the summer, we did this in 1976. In the summer of 1977, people had realized that the one-loop beta function is 0. And then Marigelman said this. He just said like that, this model is finite to all orders. He could say things like this in private. He would never say it in writing. He was so dead nervous about what he was writing. But there he could say it like that. So he even commissioned people to check it. And it took 3 months before these people had checked the 2-loop. And another 3 years before people had checked it to the 3-loop level. And this is Daniela Zanon was a real hero. They worked in component form. They had 600 diagrams to solve. Here they used a superspace technique with 53 super diagrams. And we were somehow hesitant to join this competition because we were not so trained in doing Feynman diagrams, and there must be some other way. And then, of course, we had gone back to study string theory. And in 1981, Mike Green and John Schwarz, from string theory, we considered the one-loop graph for 4-spin 1 and 4-spin 2 particles. And we got this kind of box structure. So we could see that the one-loop diagram in these theories are very, very simple. It's just exactly what you need for perturbative unitarity. And to me, it looks like a phi-cube theory. So I was thinking very hard, how can I find a formalism which implements this, which I can use to check the higher order perturbation? And as often in this case, I thought I was doing something which I didn't do, but I was following it up. So I was really going into this theory, and I was doing it in a very specific gauge. We had the one that we have found in string theory was very much working, Lycon gauge. So we took the plus component, which is the 0 plus the third component of 0, and we choose x plus to be the time. Dirac told us you can take any time, any direction within the Lycon to be the time. And we introduced projection operators on the fermions, like this. And by doing that, we could eliminate half of the fermions, and we limit the A minus, since they satisfy kinetic equation. And we reduced it to write the theory in terms of A and A bar. These are the two helicity components of the vector field. We have a spinner which has an index here, which runs between 1 and 4. It's the SU4, called the R symmetry. And we had scalars of this form. And in doing that, we could also introduce something we can call a superfield, which has, it starts with the helicity 1. Here's helicity 0, helicity minus 1, helicity half, minus a half. So this theory contains all the physical degrees of freedom of this theory. And we could write down a Lagrangian, a simple kinetic term, a simple 3-point, and a not too difficult 4-point coupling. So this is here, and note that there are no summation over any indices here. So this was the action we found. And by doing that, we could start looking at Feynman diagrams. I think I skipped that, and it's not so important. So one can do to to look at the perturbative finite, you look at the diagram like that, and you check what is the naive divergence by power counting. And you can find that every diagram like this seems to diverge logarithmically. And then what we can do was you can go through every case, so to speak. I mean, either you had something like looked like 3-point coupling here or a 4-point coupling coupled to the group. And by checking all these, well, we could find that in every case you can integrate out one momentum, and in this way the integral should be finite, and you have to use some theorem by Weinberg, by which you can do that. And so in principle, all the diagrams in these formulas are finite. Not only the beta function, but every diagram here. And I should say that at the same time, Stein and Mandelson had a very similar proof. This was in the era. Also, the covariant proof was also provided by these people. And there were other, this was in the era. People were doing indirect proofs. But so it was rather clear that this was a theory that was finite. So it was not a theory with a running coupling constant. It's a theory with a sitting coupling constant. And as such, it's conformally invariant all the time. But what can you do with the conformally invariant Young Mills? So I went back to Murgam and I said, you were right. It is. And he said, you must have a scale. This theory is useless. It isn't scale. And it took, some other 14 years or whatever, 13, 15 years, before Maldacena provided us with the ADS-CFD duality, in which, the conformal weights of the n equals 4 theory could be used, as a scale for this theory. And n equals 4 in the Young, it showed that n equals 4 in the weak coupling is a superstring on ADS times S1 in the strong. So this was one of the most amazing results. And I thought that this was the most cited paper. Now, I think it's only the second now. And the other is in another rather different field. But suddenly, that this theory that we have been sitting on there with a sitting coupling constant could be used to connect to strings, to gravity. And it's a beautiful way, and it's been checked over, the last 18 years or so, many, many times. So the theory that we once discovered, which came out through this very random, suddenly we're coming back to having a role in gravity theory. So n equals 4 Young Mills knows about gravity theory, and we will hear more from Henrik later on, so I'm not going to say so much about what's happened after that. He will take over. But let me just show you that it's connecting in so many ways between Young Mills and gravity. Let me give you another example which happens in this case. In our way of doing, we can write n equals 8 supergravity also as a superfield like this. Now over 8 thetas. You start with helicity 2, and you end up with helicity minus 2. Something has happened here. No, it's a del plus square, yeah. If someone is really, you might wonder, yeah, I'm essentially finished. I have 1 over a derivative. Think about that as an integration, or Fourier transform it to momentum space. I'm not going to spend time on techniques here. Then it turns out that this n equals 8 field is essentially just a square of the Young Mills. And this is something that Henrik will talk about. So I shall cut myself short here. So what I want to convey to you is that the n equals 4 Young Mills is really at the center of fundamental physics. It knows about gravity and the superstring. And it's the most symmetric and, in a way, the simplest Young Mills theory. But in perturbation theory, there are so many cancellations, and you only get the bare bones of what you need. So somehow, even though it's so simple, I would say that all the fundamental physics is buried into it. One just have to continue to dig. And this is, again, you know, I wanted to end by saying that this shows, you know, that the concept of Yang-Mills theory is so rich, and it's so filling up what the basic physics. So it's a miracle that we know so much about fundamental physics. So I should stop there. So.
Is the tachyon still bad? I mean, can you have a model with a virtual tachyon party interaction, like in kind of transactional interaction? We have a future past symmetry, which could go up into collabial mirror symmetry. So it's just a virtual way to adjust the computation.
No, I mean, I didn't say that, but there was another development, and this was Gliozzi, Oliver, and Schack, that they could show that one can systematically project out half of the sector, the one with the tachyon in it. So in the superstring theory, there are no tachyons. It starts with massless particles. And these massless particles by themselves satisfy Yang-Mills and supergravity.
I read somewhere that people say that the before Yang-Mills theory is Isaac model of the.
Well, he said it was the hydrogen atom, and some people may even say that it's the harmonic oscillator of the 21st century. I think it's more than the harmonic oscillator. But Isaac model is another. The infrared is the same as in ordinary Yang-Mills theory. No, I mean in the same sense that people don't worry about the infrareds in QCD. It's exactly the same problem. Supersymmetry doesn't do anything to infrared.
I was curious about what you mean by knows about. So it knows about gravity. So then who knows about supergravity? Is it super anymore?
No. Well, actually, I should have said knows about supergravity, and supergravity knows about gravity because you can throw away all the other fields than the graviton. So that, in that sense, that was a bit sloppy. Okay.
Okay. There's no questions. Thanks to the speaker.